So the last speaker is Marius Junge from the University of Illinois State Urbana-Champaign, and he will talk on relative entropy and Fisher information.
Yeah. Well, thank you first of all for the organizers for actually, organizing this beautiful conference. We will talk about this more, but what is really amazing is they essentially prepared all the background for me that essentially I don't have to work anymore. I could just go home and just make some comments, because everything in terms of why is this interesting, where's the operational meaning, where I always have a little bit of a weak spot, that I cannot answer, but they were answered before, so this is great. I mean, you answer the questions before they're asked. Incredible organization. I'm really pleased. So that's the first thing. Then thank you for the audience. I mean, I know how warm it is outside. It's Urbana-Champaign kind of temperature and humidity, wonderfully fitting to this talk, so I appreciate you being here. And so I will talk about relative entropy and Fisher information, and I have to tell you that, I mean, I learned some of these things relatively recently, and they also connect to stuff which I did before. What I really find fascinating is that with some kind of motivation from quantum information, you can actually ask questions about classical dynamical systems which you don't know the answer to, and they're as simple as looking for matrix valued functions on classical dynamical systems. And if you understand that there are some people doing geometry which are looking for bundles on vector fields, I mean, matrix valued functions are not that bizarre, right? I mean, for us they're not, but even for a geometer, looking at a matrix valued function is not completely out of the question, and our problem will be exactly around that topic. So I have a plan. Probably this is more like proving I have a plan, so we have to go through a couple of topics. What I want to stress here for the plan, the only thing which is sort of important, is I want to start with the Wasserstein distance, because the whole picture here is that mostly my motivation comes from some kind of geometrical background. I mean, that's where we have to start to understand this approach to the problem, which we already know is the hard one. The hard one is to find some kind of Fisher information entropy production estimates for these new quantum systems, which we have just recently seen is kind of highly desirable. On the other hand, I think I will make some simplifications by assuming that my ground state is Maxwellian mixed, which is kind of totally inappropriate for that problem. But it's, you have to start somewhere, right? I mean, so we want to see where geometry can kick in and help us, and that's what I want to start with. So Wasserstein distance is defined for, originally really for two measures on Rn, and you define the p Wasserstein distance as the infimum. And here, I mean, this should have been Rn cross Rn, right? So the point is that you actually take two copies of Rn, you look for all measures on the product space and calculate the pointwise distance, and then you take the infimum over all probability measures, of course not an arbitrary probability measure. If you restrict to the x side, it should be your one, and to the other side, the other one, right? So we're looking for marginals in the x side is mu, and the other one is nu. And more generally, you should even not really think of d of xy. I mean, in principle, the idea is much more general. And this is beautifully written in these papers by Otto Villani. So you take a cost function, and then you want to optimize that. And then you have this incredible infimum, and you just don't know what to do, okay? So that's the first thing. And then they start to actually produce, and that comes from fluid mechanics. They write down some Lagrangian so that you actually find the path which connects the two, right? So if you find an infimum, the best way is to find the path from x from one measure to the other. And then if you go along that path, that probably should achieve your infimum, right? So this is the way how you want to do that. And that's the general philosophy. And as it turns out, finding that path is highly complicated, and you often do this first in a finite dimensional setting, and then it's really, this is called, if you hear about an optimal transport plan, that is the concrete way to solve this problem of, this mysterious infimum. Yeah? I have to tell you something else. For commutative measures, you can just take the product measures. In the quantum operator algebra community, there's this work by Riefel on quantum metric spaces, where he has two, he wanted to prove something like matrix algebras converge to a sphere, okay? One is very non-commutative, one is very commutative. And then the biggest question of all for them was, okay, so what's the product we have to consider? Because if they're not on the same space, right? I mean, you have matrix algebras, you have functions. What's the product, right? And they have struggled with that problem. And one has to say, I've tried to understand some of the definitions. They have struggled with this problem for a long time, and then they came up with more and more elaborate definitions. In fact, it's a definition jungle, but in a more non-primitive setting, whether you should really talk about a product space or a free product space is completely unclear. It's just one of these mysteries. However, and that's the beauty, if you think of a path, then you can limit yourself to certain densities which are kind of canonical, and that's exactly what's going to happen and will save us from this kind of general obstructions. So let's go on. The easiest case is p equals 1, and then there is this wonderful Kantorowicz-Rubinstein duality where you can somehow solve this problem by first introducing this object where you take the supremum of all Lipschitz functions. So Lipschitz, of course, refers to the metric. So we have to be absolutely clear. We have a measure space, we have a measure, a probability measure, and we have a distance, right? So they call this measured Gromov-Hausdorff spaces or something like this, right? So and then you start to understand if you want to prove this equality here, then this means you have to exhibit a probability measure which corresponds to this function, and you exhibit that by finding a path, and that's this famous theorem. Good. There are many questions about this optimal transfer, even for very nice functions. So if you have a measure, so imagine you have a measure on your unit ball, and here's a Gaussian measure, two probability measures. You want to find an optimal transport, right? Or even you have two sets. You want to find an optimal transport, right? So then think these things are smooth things, then you somehow expect that optimal transport will be smooth. And then you realize that, no, it won't. And then they have theorems of, Caffarelli essentially writes an Arnold's paper proving over 20 pages that with certain smoothness conditions, these transport maps are smooth. And these are 30 pages of elementary estimates. Caffarelli, that's not a nobody anymore, right? They worked on this very hard. And what Otto Villani did, they essentially moved away a little bit from this kind of generality and relaxed all conditions on smoothness and looked at it more from a eagle perspective. And that's why this starts to work. Okay, I think I told this. So I cannot draw a picture for optimal transport. I'm just unable. But I can draw a picture for Steiner symmetrization, which is a similar idea, but for a different cost function, right? So let's do something simple. There's a T missing here, yeah, right, Mr. Steiner. So we have a convex body, and we want to move to a sphere, okay? And because we want to prove our isoparametric inequality, that the volume, suitably normalized, is less than the area, where the extreme case is the sphere. So this gives you a good idea of what such a map could look like. So you start with an arbitrary object and you do Steiner symmetrization. What does it mean? This guy is not symmetric. This is longer and this is shorter. In every line, you take here the average between the two and record it, right? So you take the average between this point and that point and record it here. And then you see that this function up is the same as this function down. So this is some extra symmetry which you have imposed to that with respect to that axis. You do this with respect to hyperplanes, right? So whenever you have a body, when something sticks out here, you move it in this direction, and what you prove is, they did it for a non-convex object, but if you actually start from a convex object, this one will be convex. Actually, this looks really convex, but of course you don't control the lower dimensions, right? So this is just a hyperplane, and this is just one direction, right? So in each step, what we are doing, conditioned onto what happens in this plane, we are moving this around. And since you're moving around, so you're just adding, just moving these lines, you're not changing the area in this particular case. So in general, you're not changing the volume because you're just, moving these sticks around. But what you do, what becomes smaller, and you have to prove that, is that the area, the boundary has smaller lengths here than there. Okay, so this is for one step, and what do they do? So this is, you can understand why transport maps in this context are complicated. They do this randomly in all directions, and then they show eventually this is a sphere, right? Because they show if you do random Steiner symmetrizations, you get a sphere because it's round in every direction, right? And then the area has gone up or the area has gone down in these steps. You have the same volume, so the area K, so that's how you prove the isoparametric inequality. But you understand that this is now almost an infinite sequence of transports, right? So, and that's an easy case. So okay, good. So this is a particular motivation, and then I just wanted to mention that there are always two ways of formulating things, either in these kind of geometric inequalities. The volume is smaller than the volume of the area when you take the sphere as a comparison, so this constant corresponds to the comparison. And an equivalent formulation is you can say that the n norm, integral Fn is less than the L1 norm of the gradient. So these are typical type of inequalities. You're comparing, this looks like a little bit like a log Sobolev. It's actually a log Sobolev, no, it's not a log, it's a Sobolev inequality, where you compare the n versus the derivative, right? So all these, we will see this frequently, that we have geometric inequalities and functional inequalities, and more recently it just has, or more recently means the last 20 years, sorry, but it turns out that the functional inequalities are actually often the smarter way to get the geometric inequalities, because you have more stability, and then at least it's more elegant, not always in terms of constant, but definitely. So let me give you two other examples for isoparametric inequalities in concentration. So I can start with the second one. So you give you a sphere, and I take A here has half of the volume, half of the area, and I take another B which has distance h. And what they prove is that this picture here is extremal, right? So, the extremal situation is take everybody on the southern hemisphere, everything around Sydney, right? And then you take the polar cap around Iceland, right? Or Greenland. And so this is the extremal situation. And if this is the extremal situation, to prove an isoparametric inequality just means to calculate the area of such a polar cap, and then you can do polar coordinates and calculate it. Right, so this, but showing that this is the extremal case is the hard part, right? So this is some kind of symmetrization. And you can reformulate that in such an inequality. Whenever I have a set, the distance from x to a, this is a capital A being h, then this here has small volume. And the concentration inequality, which corresponds to that, is to show that F minus EF here is, you have to take a mean zero variable, if not this doesn't work, is less than square root of p times the norm of the gradient, but now with the L infinity norm. So these two things are equivalent. And there is an inequality which is even stronger, which I like. This is this geometric version of Talagran's inequality. If you have a measure space and the distance, you say that geometric Talagran inequality is satisfied for some constant. If the distance between two sets is larger than a, then the product of the measures is less than e to the minus h squared over c. So concentration follows from this. Just think of this being 1/2, and you get a constant 2. But this is a very symmetric formulation, right? You see the symmetric formulation is very favorable because you. By the way, if you want to read more, Terry Tao has a blog, right? He did this, and it's very nice to read, and he also tells you why he wants to do that. The first examples which were studied is 0,1 to the power n and 0,1 to the power n. Continuous and discrete case, and here you take the Hamming distance. And if you look at the second thing, this is used in computer science. I think it's actually really used in some parts of machine learning, but I don't want to dwell on that. But they look at this Talagran alpha 2 convexity. They find a way to actually use this to prove concentration inequality. So, and even if at this moment you don't see the connection to circuits and whatnot, concentration qualities are useful for many, many purposes. So I hope in that regard, even it's not too concrete, you will find something here to take away. Good. Relative entropy, well, we have talked a lot about this. Here it is. Okay, yeah, that's the point. So I'm cheating, okay? So like Dennis Petz, I do like phenomenal algebras. That's where I learned this stuff. So I will make my life very easy by assuming that M is a phenomenal algebra, so faithful normalized trace. Okay, so I don't know, many people don't like that. But there is an important remark. Let me do first the example. So commutative probability spaces and the integral, that's an example. And matrix algebras also are examples, right? So this is my next example, and then I normalize the trace. And then you can rightfully object that, if you define relative entropy, you use the trace. The point is, for relative entropy, if you change the normalization of being a state, the relative entropy does not change. So entropy, yes, you know, sign goes through the roof, everything goes through the roof, but for relative entropy, it doesn't matter, right? That's always the same. I mean, you're not changing the signs, you're not. So relative entropy is more stable in that regard. And so whenever you could replace my trace by your trace all the time, as long as you never write down an entropy, but only relative entropies, okay? Then we're good. So in that sense, you shouldn't be worried about that. And so the geometric Taylor-Grand equality follows from this inequality, the Wasserstein-1 distance is less than a constant times this relative entropy, and we should do a proof. So let's do a proof. Yeah, so we have one set. We normalize that to be a state, right? Because this is an inequality for states or for probability measures. So these are two probability measures. When the sets have distance h, the Wasserstein distance of these probability measures is bigger than h. That's actually very easy to see. If they have distance h, you can find a Lipschitz function, which is 1 here and 0 there, right? This is typical Urizen type construction, right? You know, and then the Lipschitz constant somehow tells you that if they have distance, you can do that with a Lipschitz norm controlled by that constant. So the Wasserstein distance obviously is bigger than h. Then you use a trying inequality with a reference measure for this Wasserstein-1 distance. We use our inequality. We use a funny L2 inequality, right? And then we get the sum of the two entropies, and now you just white square that, and then you have here entropy, and for a particular thing you get that the entropy is minus ln the measure. So you know, then it's just algebra, as we say, right? So this is how you get this inequality by a very brutal application of triangle inequalities. It's rather brutal, right? But still very powerful. And what I have to say is that, of course, Taylor-Grand did not only prove his concentration inequality, he really proved something for the Wasserstein-2 distance, and that's much harder, and we all know that's a completely different story in the non-primitive case, and that's what I'm going to tell you, right? So why is Wasserstein-2 distance a different story? But I think I want to be fixated a little bit about Wasserstein-1 first. That's a little bit easier. Okay, so here, this is something I'm been pursuing for quite a while, and this also exists in the commutative literature. What I'm saying is that, look, I mean, before we have a measure space and a distance, in a totally general context, what is that supposed to be? Well, you should probably have an algebra, like my von Neumann algebra, a trace. And what is the distance? For me, the distance is replaced by a generator of a semigroup and some kind of object derived from that. That's what I want to explain. So to make my life too easy, but you know, it's warm enough, I will take a self-adjoint map on a finite von Neumann algebra. That's super reversible. That's kind of, in that sense, you know, from a quantum info point, it's a bit of cheating, but it's already hard enough. So let's start there and then do something more later. Okay, and then if you have such a semigroup, there is this wonderful Bakry-Emery theory, and the first thing you learn is there is this gradient form. In fact, the first thing you learn is there's a carré du champ. I tried to sell the carré du champ on the American continent without success. I changed to gradient form with a little bit more success. At any rate, I'm just doing it anyway. So carré du champ didn't work. I mean, just that's too French. So here it's, so we take gamma a of f1 f2 is a of f1 star f2, f1 star a of 2 minus a star of f1 2. So there are some typos here. I apologize. There is, despite this typo here, there is a real problem. If you have a generator of a semigroup in some infinite dimensional case, you usually cannot assume that the product is again in the generator. Real big problem. There's a tremendous of work of Sauvageau and Cipriani who just cleared that up. In which sense can you make that? So there's work to make that little default, to solve that. For infinite dimensional system, for matrix algebras, there is no problem. So, yeah. So this is the gradient form. Let me give you two. And then I define the intrinsic Lipschitz norm simply as the Lipschitz norm is the gradient of f1/2, gradient f star. So usually you could just take self-adjoint objects, but you know, if you happen not to have self-adjoint objects, it's at least well defined. And the examples on Rn, if you take the Laplacian, that's the gradient form is really the inner product of the gradients, right? So, by the way, you see that the Riemannian metric kicks in form of the Euclidean. And then if you take a graph, a finite or infinite graph, and you define first the gradient form, that's for every point you take, I think we had this in the problem session, right? So the gradient form is that for every x, you count the edges which are there, and then you take the sum of the squares, right? The sum of differences. That's the gradient form. And then you can calculate the generator from that gradient form. I leave that as an exercise, right? So in that sense, they really have a canonical geometric meaning as either being really differentials and looking at all the directions in the continuous case, or looking at all the edges which you want to connect to in the finite case. So that's the gradient form. But I just insist that this is intrinsic because it only depends on the semigroup. I don't have to assume something extra on the space. Good. Yes, and then I define Wasserstein-1 distance as the distance for between two states is rho minus sigma, and that is just the supremum over the forms with gamma ff less than 1. Don't forget gamma ff less than 1 is in the commutative case simply saying the Lipschitz norm is less than 1. So and that's the philosophy, right? So you replace this here by, this is my new Lipschitz condition. So my Wasserstein-1 distance is defined as by duality from the Lipschitz. I take duality with respect to the Lipschitz function, like in the Kontarovich. I'm copying, sorry guys, I'm copying, that's not very clever. I'm copying this definition here, right? The supremum over f of x d mu of x d nu of y, but I take the sup over all Lipschitz functions. I redefine what Lipschitz functions are and then take the same sup, right? That's my Wasserstein-1 distance. And so then I can say that a semigroup satisfies lambda w1 with these funny constants. They put this traditionally here. If the Wasserstein distance, the one Wasserstein distance is less than the relative entropy. Now here I write E of rho. What is E of rho? So the main problem we have is because I like to use matrix valued functions that are not always ergodic. I'm neither primitive nor ergodic. I'm not assuming that. If I'm neither primitive nor ergodic, I have to use a conditional expectation on the fixed point algebra. That has been explained before, but just to be on the safe side, conditional expectation for matrix algebras is not a monster. You have a unitary group. You average over the unitary group. That's your conditional expectation. That's why it's called expectation, because it's a real expectation. And this conditions, right? So this is identity on the commutator of the group, because if you put here a density which commutes with the group, you're not doing anything, right? So if you see conditional expectation, think of a group action, and then you take this average over the group action, and that conditions on the fixed points of the group action, those which commute. So conditional expectations are very natural. For finite dimension, for infinite dimension, that's a different story. So, but let me also mention that I have this complete version. So I wrote that under the carpet here. We have seen this before in Ivan's talk. So as usual, whenever I don't know what to do and I don't know whether this W1 constant might not be stable under tensorizing an innocent system. If I tensorize an innocent system, I do change my conditional expectation. That's what I want, right? Because this is the candidate for the fixed point, right? So if I do that, then I will just solve this as a complete Wasserstein distance with parameter lambda if it's true for all additional heat paths I want to couple, but I don't want to act on them, right? I act on my, so this is and again, for this purpose, it's kind of convenient because we don't have these stability question problems. So here's a little bit of a tensorization result. So we have this complete Wasserstein-1 distance, and we give ourselves generators. So here I'm working on the tensor product, but I have to set that could be a little bit more general. And then you can estimate the following thing. You take an f with conditional expectation is 0, and then we calculate this trace here, and you do get this term back, rho e rho, what we are expecting. But we are not getting totally the intrinsic distance. We get something slightly bigger. We take the L2 sum of the individual differences. That's something which one can prove, and the point is I'm proving this for a non-tensor product rho. So in that sense, it's a little bit beyond identical. I mean, if you do this for a tensor product state, that's very easy. If you don't do it for non-tensor product states, you have to use the martingale properties of relative entropy. And the martingale properties of relative entropy, they only show up if you actually do these conditional relative entropies, which one has to use in this context. So that's kind of a nice thing. Martin did something in this context, and she proved that to reprove Talleyrand's inequality for Hamming distance. And that becomes a very short proof. And this sum here is not a problem because they replace it by square root of n and then normalize correspondingly. So there's a normalization trick. And so this little trick, if you do the 2-point inequality for a 2-point space where estimating this lambda is actually easy, then you get it for higher systems. So this is a very cheap trick to get some of these tensorations. It's just a little bit weaker than I really want to have, but it's good enough to do the Talleyrand inequality for Hamming distance, which is also not bad. I mean, that's what, if ever, they will use in computer science, right? So, so the intrinsic Lipschitz norm would just be a little bit better. You take this norm inside instead of outside, and that I don't know how to do. But with this Wasserstein 1 distance is a mild assumption, that works pretty well. So in that sense, this is, slightly beyond I.I.D, I would say, right? But okay. So we have a nice application. Take a generator of a self-adjoint semigroup on a finite dimensional matrix algebra. Then these tensor products always satisfy some version of Talleyrand concentration inequality. So if you're willing to choose the right definition of Lipschitz functions, you have Talleyrand's inequality like in the 2-point case for an arbitrary generator of a self-adjoint one. For non-self-adjoint, I don't know, right? So that's widely open. But this is that's so far for an arbitrary generator the best I know, right? So, I mean, yeah, we will talk about examples later, but that is new. Okay, here comes the Fisher information part. Again, in my generator setting, Fisher information is really easy to write down. It's trace of A row ln row. My A is self-adjoint. I don't have to worry whether I put it to the left or to the right, which is nice, right? So that's okay. Of course, this has many other names. Entropy production, which comes from the fact that if you differentiate the relative entropy of TT row with respect to the fixed point state, the expected fixed point state, then this is just minus f prime of 0. So this is why it's called entropy production. Of course, we have seen that there are many divergences, and if you have many divergences, then there are many Fisher informations. I took the most canonical one, so the logarithmic one. Okay. And then I should have usually written here MLSI because that's the modified logarithmic Silverlove inequality. Now, if you go through literature, sometimes Otto Villani, they don't write anything. They just write LSI, and they suppress the M. So I said, okay, if I write a new paper, which I will, actually, my paper is on the archive this week, right? So I just call it FLSI to be sure that it refers to Fisher information. That's for me, right? I can remember this is Fisher information, and I use the Fisher information and not the energy form. So I will solve something has FLSI if I have this inequality, and we have seen how that works before, that this gives these kind of exponential decay. So we want to have this exponential decay of the relative entropy, and that is exactly equivalent to having this inequality here. And right, same trick as before. If I don't know what to do, I don't know the tensorization property, I call it complete LSI if it tensors with a dummy. That's just a definition, right? And that's again, like we started from bounded to completely bounded, positive, completely positive, LSI, complete LSI, right? So it's a scheme, right? But it is nice because now it has the stability property. If A and B have lambda CLSI, so does has the generator of the new semigroup, which you probably all remember as A tensor 1, 1 tensor B. Yeah, so that's kind of making it possible. If I can control this constant, then I have at least the identical, the tensor copies, I can control them. Only problem is I have to show this inequality. Good. Examples, well, we have seen that if I take one of the nicest generator, but I think this is not nice in the sense of classical systems, because this is not a generator which is smooth. identity minus conditional expectation, identity minus the integral. It's not a smooth generator, doesn't satisfy, doesn't correspond to a second order differential operator. So in that sense, they will not like it. But if you calculate the Fisher information for identity minus conditional expectation, it's the sum of these two terms. And then, of course, this is bigger than one of them by the positivity of relative entropy. So, identity minus E is the generator which automatically satisfies one CLSI. And then you can tensor. And the tensorization results we have seen so far probably all can be deduced from this little fact plus the lemma before. Right? I don't think we have new ones beyond that, right? Before. So by the way, if you do this in the two-point space, they call it two-point function, and that has a long tradition in hypercontractivity. They start from a two-point inequality, then they do tensor products, then they do central limits, then they have Gaussians. If they have Gaussians, they can do spheres. If they can do spheres, they can do groups. If they can do groups, they have certain manifolds. You can almost do Ricci curvature bigger than 0, but only on that's kind of there it starts to be different. But for a long time, many results were all deduced from this one two-point inequalities. Many of the classical results, except for geometric ones, they were all could all be reduced to one simple example and the stability properties. So they're important, and we want to go a little bit beyond that. We have seen examples, and then we have also seen that FLSI is positive. And then, of course, the big open problem, we have no idea, is whether every matrix algebra, every self-adjoint renormator has CLSI. I want to have a constant bigger than 0, and that would just be wonderful, and I don't know. Okay, and in that sense, since we don't know that, we are even pre-I.I.D, because I think that's what something, this would be the I.I.D case. You take tensor product of a nice object, and that should still be we don't know. Okay, so here is the Wasserstein 2 distance. First of all, they show that if you have this modified logarithmic Sobolev inequality with the Fisher information, then you also can estimate the Wasserstein distance. Now, I think for me this is the 2 outside, because I defined it with, they often, they're tricky. They define this with a 2 lambda instead of a lambda, so Ivan knows that problem too, right? You have to be careful. The constants are not always the same, right? So some definition, I think the way I have to do it here is with a 2 outside, but it's not important. So modified log Sobolev implies Wasserstein 2 distance. If you have Wasserstein 2 distance, you have Wasserstein 1 distance, you have geometric Talleyrand inequality. Okay, and then of course the whole point is, how do they prove that? They prove it by finding an optimal transport plan for the Wasserstein 2 distance. They differentiate along this plan. They use the log Sobolev inequality there, and then they deduce the estimate. It's a very geometric argument, which only works by really knowing the transport plan. And it also works because you have to do a finite dimension approximation where you can do that, and then you have to do some weak star limit. Because as I said before, continuity is not guaranteed, so you have to be very, very careful. And the paper there is very, very explicit about this, but also very inspirational. Okay, so the geometric aspect is you understand this FLSI as a convexity condition on geodesics. So I will talk about this later a little bit more, so we will see that. And they have to use in the ergodic setting. If not, it wouldn't work. And then there's this work by Carlin and Maas, which essentially for a generator on a finite dimensional C-star algebra, they do the same thing. They prove the same theorem, with the only difference that they have to invent the right Wasserstein distance. Right? This was not a God-given thing. This is something they really had to work hard for. But in this sense, it's easy to state what they did, and we have to understand this a little bit better. But we'll do this in a second. But the corollary is that, so if you have lambda FLSI, then you have this Wasserstein 1, and you also have the geometric Talleyrand inequality. So concentration inequality all follow once you can. So the goal is to have this FLSI, right? So this is clear. We want to have that inequality if possible. And here is an overview of all the. Oh, okay. So this is not the latest version, because here is a long list of of people who worked on that, and that is momentarily not on this file. Yeah, some of them are in the audience. It's a long list. The last one is Niliana, so the rest is all before. Okay, so Cambis, Ivan. Well, I mean, as we just learned, David Garcia Perez. Anyway, this is a very long list. I should say it started probably with this paper by Zigalinsky. There's some previous work by Lindsay and Davis, who understand these semigroups, and then Temme, of course, Temme and all his collaborators, and Qubit. And anyway, so there's, sorry for that, there's a long list. It will be on the final version here, but at the moment it's not there. And of course, many of these inequalities were well known. You know, Temme proved something from here to here. This was Cullen Maas. Some inequalities here were proven by some subsets of the non-existing orders on this blank set. So there's a lot of work before. Okay, so let me start with the problem, and then we will come back to the geometric interpretation. The problem is this Rothaus lemma. So in the ergodic case, if you have this inequality, trace f squared log f squared is less than the constant times f a star, this is called the energy form, then you, for mean zero elements, then you can actually prove it for non-mean zero elements. That's the Rothaus lemma. So you have something for non-mean zero elements, for mean zero elements, and then you can prove it for non-mean zero elements. And in the ergodic case, that works out perfectly fine, and that's why the hypercontractivity works. In the non-ergodic case, it just doesn't work anymore, right? So by the way, why is it good in the ergodic case? Because for this part, you can use spectral gap. So if you have this kind of estimate, you can plus spectral gap, you get the full estimate. And then there is this problem from going from this energy form to the Fisher information. We have heard about that before. These are these, you know, in the self-adjoint case, that's very easy. You know, this LP regularity, which was studied by Zigalinsky, and you know, they worked on that and others. So in the ergodic case, this works, and in the non-ergodic case, it completely fails. I mean, you know, the step from here to here fails as much as you want. I mean, I found we have independent examples, which is kind of funny. I have one where I have to put the dimension as large as I want for this type inequality. And for this type of inequality, I get a violation of order log n in dimension n squared, which is, you know, given that this is a normalized functional, that's kind of as up to a factor 1/2. It's the worst you can get, right? And Ivan has some other counterexamples. So this in the non-ergodic case, this step here is a no-go, right? And then you have to choose either modify hypercontractivity or forget hypercontractivity. You have two choices because you can't use it literally anymore, right? I think some of them have decided to modify it. I decided to forget it. So the tools we use here are derivations. So this is a general fact about CP semigroups, self-adjoint CP semigroups on von Neumann algebras. There always is a derivation. Did I write down what the derivation is? Probably not. Yeah, so that's the derivation. And if you do it in this left-right notation, it starts to make sense. So for every semigroup, there is a derivation. And if you have a derivation, and that's the point which we have to prove, we actually have a derivation with another finite von Neumann algebra, and then if you take the conditional expectation, you get the gradient form. If you want to understand what that means for a Lindbladian, my Lindbladian have a different sign, so this is how they look like, right? So you give yourself some self-adjoint operators. These are the self-adjoint semigroup operator Lindbladian, and then they simplify a little bit. ak squared minus 2ak. And the derivation is just given by some commutators. But if I want to find the right norm, I actually have to formally introduce some, that's cheating. I have to use some semicircular Gaussian random variables that gives the right norm. But that's just because I want to extend this to matrix valued functions, and then I have to use a trick to introduce the right norm. But that's just cosmetics. The point what I want to have is that I want to define the derivation so that the norm of the derivation corresponds to the Lipschitz norm, right? The right-hand side is the Lipschitz norm, so I want to have that the norm of the derivation is the Lipschitz norm. And even that is not known if you take the standard derivation in commutative spaces with matrix valued functions. Yeah. So if you don't do this right, this does not extend to matrix valued functions even in commutative geometry. So that's what we have to do. But we have a connection between the derivation and the norm. Then we can define something like a tangent space as this space generated by delta of m times m. Now for every density, since our m is contained in m hat, we can define this non-symmetrized product, the corresponding inner product. And then for a function on the state space, we can say that it has a gradient. I mean, here I'm essentially following Karl and Maas. So we are defining a gradient. And this gradient definition, if you see it the first time, looks really weird. And then you look at it again and it still looks really weird. And then you look at it again and then you realize this is just a fancy form to write down the chain rule. Yeah, you write down the chain rule involving the metric which you have to do. So I think that's the best thing you should remember. You should not remember the formula. It's if you have to write down the chain rule at some point, you don't have a choice. That's the one. Okay? And then, so if you take a nice function, the relative entropy, the gradient is delta of log rho, and the norm of the gradient is the Fisher information. So that is the puzzle which Karlin and Maas solved, right? So they came up with a definition of some inner product on such a larger space which corresponds geometrically to the space of differential forms in some way, some kind of differential, abstract differential forms. And then they found this right metric on that form so that these two equations are all true, right? I mean, if you understand that that's what they wanted to do, then you really don't have so much of a choice. And this modified product here was the right choice, and that has a lot of motivations, right? I mean, they knew that by looking at previous examples. But that is the puzzle they solved, and then suddenly everything works out. So I try to explain here why this is the right gradient, the chain rule. I think what I said is better, and then you actually can define. So this is now important. So you have the state space. Here's your state space, right? You have geodesics on the state space, which are supposedly somehow related to the action of a semigroup. So here's your state space. If you have a state space, if you think of this as a Riemannian manifold, you have a tangent space at every point. But if you differentiate a function in the state space, the derivative is an element in the algebra, right? So we have to connect the elements in the algebra with the derivatives coming from this metric. And again, the right choice is this choice. So the norm of a derivative in the algebra is the infimum over the norm of the vector in the tangent space, right? Where I take the infimum over all ways to understand this as a derivative of a function, and that's the right definition. So I mean, I could explain more, but I'm just telling you this is what I understand is the correct definition. Take some calculation, but this is the right one. And once I have this distance, I can define a Caradero-Dori or Wasserstein distance. I take the infimum over all paths. In every point, I calculate the norm of the derivative in that path, and that's how you have it. You take the infimum over all that path, and that is what they classically call Caradero-Dori distance for a sub-Riemannian manifold. So think of a manifold where you strip away some directions. Okay, so this is the right distance. And then they proved that with this distance, they have this estimate, and they proved that with this distance, they have Wasserstein 2 following from FLSI, right? So it's a very geometric construction. And then, again, we want to have examples, and that was the hard part of the problem. How do we actually get examples? And here's how we get examples. We start with a Lie group. We start with a Lie algebra, and we take what is called a Hermander system. The Hermander system is simply a system which generates the Lie algebra, period. A Hermander system on a Lie group is a set of directions, and then you can associate with these guys vector fields. So let's associate with these vector fields. If you have vector fields, you can define Laplacians, sub-Laplacians. So this is a sub-Laplacian. Usually you would consider the Laplace-Beltrami, that is given by a basis of the full Lie algebra, but taking subsystems. Okay, so this is a Laplacian. And then there's something nice. There's some deep work by Stein and Rothschild. They proved heat kernel estimates for arbitrary sub-Laplacians. that's a good starting point. If you get this for free, you should not, heat kernel estimates are always good. And then we also have a spectral gap following from that work for free. And then we found something nice, the so-called Chow-Rachevsky theorem, which says that if you have a sublaplacian on with a remainder system, this still has finite diameter. It's highly non-trivial, right? I mean, usually if you have a Riemannian manifold, you take all directions. Now take away, you take only 3 out of 5, but you still have finite distance. It's a compactness argument, really beautiful. So with this distance, we have still finite distance. And then we prove the following things. If you take heat kernel estimates plus a spectral gap for A, then we prove not for A, but for A to the power theta. If A is a generator, A1/2 is a generator, A to the 3/4 is a generator, some kind of functional calculus. But, that's what you do in ergodic theory. They know how to do this, right? So if you take A to the theta, this also satisfies a Strangler property, in particular lambda CLSI. And this Strangler property is actually that we can compare some gradient forms. We can compare the gradient forms of identity minus conditional expectation with the gradient form of the generator, right? So we have this very strong property, which you can prove for A to the theta, but not for A. It's kind of a little bit bizarre. I think so far, even in the commutative literature, I've never seen that an A to the theta is much better than A. They just overlook that, right? But we have, for A to the theta, we have this stronger property. That's our first result. Now take a generator on a semigroup of on a finite dimensional matrix algebra, then L to the theta also satisfies this property. That's what we can prove, and I will show you schematically why in a second. And then the open problem is whether, remove the theta, do we still have lambda CLSI? I still don't know that. But what I can prove using this Rachevsky theorem, that every A has lambda CWA1. So every A has at least some Talleyrand inequality, also following from the same idea. And the idea is very, very simple. You take you take these generators from the Lindbladian. They're there. You have a self-adjoint Lindbladian. Take these generators, and then you show that there is a group for which these guys are a Hermander system. There you have to show that. Okay, these guys. There is a group, and once you have that, you can apply everything, because what happens is, I have a picture just here. So here's your group, right? And you have this Hermander system, which are certain directions. And then if you take the group representation, if you have a group representation, you can differentiate the group representation. So you start with a group element, you think of this as a one-parameter group, and then you write a one-parameter group in the matrix algebra is e to the ita for some aj. So what I'm saying is I give myself aj, and then I can find the groups and the xj's. Yeah, so I do it kind of reversed engineering. And then what happens is I have here the sublaplacian, but the sublaplacian translates into exactly my Lindblad generator, right? So that's what's happening here. And then there's something nice. You see, I have here this I have all these geometric objects, a Hermander system, a Laplacian, whatnot. And if I tensor identity on a matrix algebra, I realize that my real generator is kind of a subsystem. There's a subsystem which is moved to itself. Right? Whenever you have a semigroup and a subsystem, every property from above translates to a property from below. The only problem I need is, this is why matrix valued coefficients are so much needed. I cannot do it with identity. I have to add some matrix algebra coefficients, and then all the properties are inherited down, right? So you prove something nice about your geometric system, you tensor with identity, it's there for the algebra. And if I combine that, then I get that, for every generator has at least some Talleyrand inequality, because it satisfies the complete version of Wasserstein 1. This I know for now. This is what I know at this moment, right? I can approximate it by guys which are very strong, because they have this gamma E property, and gamma E property, by the way, implies immediate return time estimate, e to the minus lambda t without a constant. Yeah, so this gamma E property is very strong, immediate return time estimates, and therefore also entanglement breaking estimates, and all of these kind of little things which we might care about. Right. And what is open is what happens when this CLSI, so the complete logarithmic sublevin inequality in full generality, I don't know. Thank you for the wonderful conference. This was incredible. I really learned a lot. And I think we should thank them.
If anyone wants to ask a very brief question or brief comment,
Yes, just very quick one. Just want to make sure your argument in non-commutative setting actually proved some Lagrange type theorem. I mean, your argument does it produce any like, for instance, the theorem like Wasserstein 2 distance less than the relative entropy?
Yes, for all these, you start with a Lindbladian in finite dimension. You take 1/2, and this has Wasserstein 2.
Okay, so your argument basically is based on the geometric argument.
Yes,
where you
I construct a Hermander system, and I mean, I construct a compact group. I construct a Hermander system. I take all this harmonic analysis information, boom, and then use it for the generator on the matrix algebra.
So obviously included the commutative setting as a special case.
Yes, and in fact, these particular better informations for subordinated Laplacian in the commutative case, some of them were not known. I mean, you know, they still satisfy, because they didn't know what is the right derivation. Yeah. A particular example who like that Poisson group on a circle, right? That satisfies 1 gamma e. And that, I think that particular immediate return time estimates for the Poisson semigroup was not known, even in the commutative case.
Right. Very good. So I suggest we thank Marius and also all the other speakers of the conference.